Hi, this is Mr. Manley. In this video I'm going to look at graphing a couple of exponential functions. First thing about graphing an exponential function, like graphing anything, is we want to depend upon a table of values. And the second thing is that in this table of values, like the table of values for a line, we only need 2 points to graph an exponential function. In fact, what we need to graph an exponential function is an asymptote and 2 points. Here's a horizontal asymptote, and that is the asymptote that every exponential function has. And what makes a function an exponential function is that it has a variable exponent. So when we have a variable exponent and we are graphing this function, we will always have a horizontal asymptote. And then from there, we just need 2 points. And there are only 4 possibilities. I gotta have a point here and a point here. And then I wanna have an exponential shape, which is a curve that increases exponentially and then falls towards the asymptote. And there is one possibility. Here is another possibility. And then we have this possibility, and we could get our 2 points like this. And that's it. 2 points in an asymptote, and the graph is going to look like one of those 4 graphs. One question that we may have is, where is the horizontal asymptote? The horizontal asymptote of an exponential function is always found here on the outside. Whatever number is being added to the exponential expression is going to be where the asymptote is. Y equals that number. So in this case, it would be at y equals 1. If I were to change that, that would be at y equals 2. If I were to change that, that would be at y equals negative 3. And if I were to have nothing at all, that would be at y equals 0. Once we have the horizontal asymptote, the next thing we're going to do is find 2 points. We want to find 2 convenient points, 2 points that have values of x that are easy to evaluate. In this function, I have an x minus 1 for the exponent. So if I let x equal 1, look at how easy that is. I'm going to go y of 1, which means substitute the value of 1 for x. And I go 1 minus 1 plus 1. Well, what's happening here? The 1 minus 1, that's 0. So I have negative 1/4 to the 0 power plus 1. And we know anything to the 0 power is 1. So I've got negative 1 plus 1, which is equal to 0. So that was a convenient value to evaluate. I plugged in a 1, and I took more lines than I really needed to there, just to go into the details, but it's going to equal 0. What's the next convenient value that you might see? Can you see something that would be convenient to evaluate? How about y of 2? And then that's going to give me negative 1/4 to the first power. You see that? When I plug in a 2 here, I'm going to have 2 minus 1 is 1. And then I've got the plus 1. So I've got negative 1/4 plus 1, which is 3/4. 2 3/4. And that's all we need. So let's graph the information that we have. Looks like a convenient scale on the x-axis would probably just be go 1, 2. And on the y-axis, I might want to go up a little bit further, maybe with my 1. Maybe I'll go up there. Okay? So I've got my horizontal asymptote at 1. and I've got 0.10 right there, and I've got 0.2 and 3/4, which should be, say, there. And that's it. 2 points and an asymptote. So I'm going to shoot off exponentially in that direction, and I'm going to approach the asymptote in this direction. Notice that we're also asked for the domain and range here. The domain of an exponential function is always -infinity to infinity. All real numbers for all of the exponential functions that you will see. The range is always going to include this value. It's either going to approach that value or it's going to proceed from that value. We see here that we are approaching that value from the negative side. So we will say that the range is from -infinity to 1. Always getting parentheses on these, because infinity always takes parentheses, and 1, an asymptote, the asymptote will always take a parentheses as well. Let's look at another one. This one might not look so comfortable to you, or you might not be so familiar with this. All we've got here is this constant. This is a constant. It's not a variable. It's an irrational constant. That is, it's a non-repeating, non-terminating decimal. And it would be in the same vein as pi. Like, I know that pi is approximately 3.14. And just like I know pi is approximately 3.14, I know that e is approximately 2.7. Where does that come from? Well, e comes from the value 1 plus 1 over x to the x. And then I'm going to use a little calculus notation here. This limit, this is read the limit as x approaches infinity. That's how we read that, or a way to read it. And what does that mean? That means let x be really large in this case. So if I let x be very large numbers, what's going to happen is I'm going to approach the value of 2.7. I will get the value of 2.7. And then as I let the value become larger and larger, I would find the other decimal places of e. But for our purposes, we'll just use 2.7. So that's all we need to keep in mind about e. I'll keep it up here in the upper right-hand corner, that e is approximately 2.7. And then we're going to go about this in the same way as we did the other one. We're still going to set up a table of values, x and y. And we are going to look for our asymptote. Well, there it is, asymptote at -4. We're going to do convenient values. Do you know what my first convenient value will be? -1. Because that'll give me an exponent of 0. So y of 1 is equal to 1/2 times e to the 0 minus 4. And of course, e to the 0 is 1, so I have 1/2 minus 4, and we'll just call that -3.5. Second convenient value, how about 0? That'll give me 1/2 e to the first minus 4. That's the way I want to write it. At some point, I want to show that that is the value when x equals 0. I can condense it down here a little bit, right? E over 2 minus 4. So somewhere I want to show that I do know that is the actual specific value of the point. But then for graphing purposes, I will want to have an approximation for that point. All right, almost done. Just gonna set up an axis here. Got to choose an x and y, or we got to choose x and y scale, right? So we're going to -4, -3.5. That's not going to be quite as far. And yeah, so I think we'll probably just go ahead with a scale of 2 here. And we'll go with a scale of 1 on the x-axis. Let's see how that works. So again, I've got this y equals -4 as my horizontal asymptote. So that'll be here. That'll be -4. And then I've got -1, -3.5. So that'll be over here. And then -3.5. So that's going to be 2, 3.5. That's going to be right in there. And then finally I have 0, and I've got this e over 2 minus 4. So probably going to want to key that into a calculator. If I had to get by without it, I could, but if I have a calculator at my fingertips, I am going to go ahead and key that in. Keying that in, I get, you see here, -2.6, approximately, for e over 2 minus 4. Now, when you key this in, there is an e feature on any calculator that you would be using, so you can key in e, but for our purposes, it would also be appropriate. It would also work out all right to key in 2.7. Graphing that point, 0 and -2.6, I'm going to be up here somewhere. And there's my 2 points in my asymptote. Get through those points and approach the asymptote. I don't love that I don't know what the x-intercept is, and my graph is making it look like it could be 1. So that's something actually for some future concepts that we do, we'd be able to evaluate and determine what the x-intercept is. For our purposes here, I don't like it, but we're just going to leave it at that for this exploration of exponential functions. And then the domain and range, as I said before, the domain is always -infinity to infinity. And here, our domain is proceeding from -4 to infinity. And that should set you up for any exponential function that you're going to find. And if you keep falling back on that, 2 points and an asymptote, find convenient points, you should be able to graph all of the exponential functions that you encounter.